For the current lecture, we'll start looking at the tides. Get the PowerPoint up here. And hide the extra bits there. Move me down towards the corner. The tides are a very conspicuous feature of most of the ocean. If you spend time near the ocean, you'll notice these changes. Due to the tides, the line between the land and water is continually moving up and down, reaching high and low either about once per day or about twice per day. Tides are a special category of wave with very long periods. Unlike the other waves that we looked at, which most of them are caused by winds, the tides are caused by the gravitational interaction between the ocean and the sun and the moon. The crest of the wave of the tide is when we have high tide. The trough is when we have low tide. Measuring the difference between high and low tide, that's known as the tidal range. Again, the period, the time between one high tide to the next high, or one low to the next low, is usually either just over half a day or just over a full day. Some places have quite extreme tidal ranges. This is one of the most dramatic, the Bay of Fundy, southeastern Canada. And you can see how far out the tide is low versus high in the two pictures here. Now, the tourist information claims that these are the highest. There are some other places that rival it, but this is easiest to get to with tides this extreme at any rate. The extreme tides relate to the shape of the bay, something of a funnel shape. So the water is kind of funneled in and out to be more extreme. And also there is something of a change that the sequence of the tides tends to reinforce itself. Here's another example of the effects of the Bay of Fundy. At low tide, in the lower picture, we have the river flowing down and towards the left side of the picture. At high tide, we're standing a little bit different spot, getting that picture. The river is actually flowing backwards, going up due to the tide pushing in. We can recognize three patterns of tides based on the period and how regular they are. Diurnal tides are ones where it's one high and one low in just over a day. Semi-diurnal tides, semi-half, so that's two highs and two lows for just over a day. And both of those highs and both of those lows are pretty similar in their heights. Our third category are the mixed tides. These have two high and two low tides per just over a day, but noticeably they are not both even. You may have the two highs close to similar, but the lows are pretty different, or you may have different highs, lows similar, or both pairs may be noticeably different from each other. Also, if you spend extended time at the beach, you'll find that the tide range varies, and this matches the cycles of the phases of the moon. So we have spring tides. These are when the high tide is the highest and the low tide is the deepest. And there are neap tides, where the highs are not so high and the lows are not so deep. Tide also relates to the configuration of the seafloor in the area. What shape is the edge of the land, and also the bottom of the ocean nearby. Here are a couple of examples of tide cycles. The first one is for Pensacola, Florida, Panhandle right next to Alabama. And then the bottom one for San Francisco. Scale here, hours 0 to 24 for both of them. So these both are showing a full day. And we can see different patterns. Up here for Pensacola, one high, one low. It's getting back to high, so one high and one low in the day. San Francisco, we have a high, a low, a high, another low. So we've got two in the day there, and also pretty obviously this low is different from that low. So one high, one low, that's diurnal for Pensacola. And two, but different, is the mixed pattern for San Francisco. One other thing, if you look at the scale for Pensacola, it's centimeters. Up 10 centimeters, down 10 centimeters, that's a total tide range of only about 8 inches. San Francisco, on the other hand, is going more than 1 meter up and down. So for that, if I were to stand at the edge of the water at low tide, just keep on standing there and get kind of bored and hungry and all, but eventually I would be totally underwater unless I stick my hand up. Here are examples of tides around parts of the US, and you see different patterns. All of them show the range from the neap tide with the smaller range to the spring tide with the larger range. But you see some, for example, a number of the West Coast ones that show a more mixed pattern. Along the East Coast, we tend to have more of the semi-diurnal, and the Gulf Coast tends to be the diurnal. There are also noticeable differences in places such as Anchorage with a much wider tide range, and Gulf Coast typically relatively small tide range. One other thing you may note, the numbers are mostly positive, not as much negative. For these diagrams, although not the previous ones, 0 is used to mean the average low tide rather than the middle of the tide range. So just be aware the numbers may be given in different ways in different sources. Again, tides are a result of the gravitational pull between the oceans and the Earth and Sun and Moon. But also there's the effect of the spin of the Earth, and there are a couple ways that that is important. For now, we'll focus on the centrifugal effect. The outward apparent push from rotation. Gravity, as long as we're not getting too close to black holes or things like that, we can stick with Newton's formula of the force being proportional to g, that's constant to make things work out, times the product of the masses and divided by the square of the radius. So bigger masses give you bigger gravity, no surprise there, and shorter distances give you bigger gravity. Moon is much smaller than the sun, but it's way closer. And so it turns out that the moon's effect on the tides is twice that of the sun. So the moon effect will be stronger, but the sun has a noticeable additional effect. Gravity pulls the ocean toward the moon and the sun, and these create a bulge towards each of those as the Earth is turning. Also, thanks to the centrifugal effect, we have the rotation, and that contributes to another feature of the tides. Focusing just on the Earth and Moon, water towards the Moon is pulled somewhat more than the solid Earth, and that's pulled somewhat more than the water on the other side. So to some extent, the water on the far side is left behind. Also, from the turning of the Earth, the combination together gives you a bulge towards the moon or sun, and another bulge opposite it. Now, of course, they're not nearly as big as shown in this picture here, but they're too small for you to see in a picture this size. So we have a rather exaggerated bulge to illustrate the pattern. And so we'll start with a simple model, equilibrium model, where we have a bulge towards the moon, bulge away from the moon, and the Earth turns under it. So different parts of the world will get a bulge of water at different times, depending on where in the globe you are. This explains why we have those three patterns of diurnal, semi-diurnal, and mixed. If you're in a place that pretty much only gets one of those bulges as the Earth turns, well, then you get one high, one low per day, and you've got your diurnal pattern. If you're in some place that gets a relatively uneven amount of the two, then you get a more mixed pattern. Some of one bulge, some of the other, but noticeably different amounts. If you're getting about equal from both bulges, that would give us the more semi-diurnal pattern. So we've got a bit of an idea as why these different patterns in the tides are happening. Here's a map showing where we have diurnal versus mixed versus semi-diurnal, as well as the tidal range, whether it's very high or small or in between. I'm not sure why they didn't pick colors that contrasted better to see things. But one thing, it's more complicated. It's not a great match for the equilibrium model. Equilibrium model is somewhat overly simple, but it helps give a picture of what's going on for the tides. What's happening with the spring and neap tides? You can see here comparisons of two places, one in Australia, South Australia, versus China. And although the pattern of tides in terms of the range and whether it's the more diurnal versus semi-diurnal is different, both of them we're seeing the spring tide versus neap tide, spring tide, neap tide at the same time. Again, emphasizing this is a pattern matching the phases of the moon. So what's going on here? It'll be easier to show demonstration, but I'll talk through it here as well. Basic idea, if the moon and sun are in a line, let's say it's new moon, the side of the moon towards the Earth is dark, which means that the other side is pointing towards the sun. And so the moon and the sun both in the same direction. Pretty obviously they're pulling the same way. And so places on Earth will have extra high highs, extra low lows because the moon and sun are working together. At full moon, we can see the whole face of the moon lit up because it's opposite the sun from us. And so light from the sun is getting to the side towards us, unless there's a lunar eclipse. Opposite, but remember there's a bulge towards the moon and a bulge away from the moon, and same for the sun. So once again, the bulges being made by the moon and by the sun are lined up, so they add up, and their effects work together to give a higher high, lower low. Our neap tides occur when the moon and sun are at right angles relative to the Earth. So this means the moon's stronger pull is going one way, and the sun's pull is going opposite that. So they partly cancel each other. And this gives us the weaker neap tides. Quarter moon refers to being a quarter of the way through the whole moon cycle. It's when we can see half the moon lit up. A little confusing, but those are words, we're kind of stuck with that. So at first quarter and last quarter, one side of the moon, what's lit up by the sun, we see half of that, And so we get the different appearances and the weaker tides. So again, spelling out spring tides, Earth, Moon, Sun are all together a straight line. New or full moon, neap tides, they're at a right angle, first and last quarter. Now, I've said a few times, just over a day or just over half a day. Why is that? Well, the moon is orbiting around the Earth. And so by the time the Earth makes a complete turn for a day, 24 hours, the moons move forward some in its orbit during that time. So it takes a little more than a day for any one spot of the Earth to catch up with the moon once more. So as a result, the whole tidal cycle goes about 50 minutes later each day. If it's high tide, say at 8 a.m. today, then there'll be high tide at around 8:50 tomorrow. At the exact time, it does depend again on the pattern of where's land and how deep the ocean floor is, or the bumps, stuff like that. So it's not perfectly 50 minutes everywhere, but that's pretty close to the value that you'll find. You can actually get clocks if you're near the beach to show the tide cycle that run 50 minutes later than a clock showing the time. As it's said, that equilibrium model is rather simple. The dynamic model of tide has some additional complexities. We're taking into account the Coriolis effect. We weren't considering that with the equilibrium model. And also, tides are equilibrium model. Again, we have the Earth turning under those two bulges of water. I didn't see any big bulges of water coming around here. So there's land. And that is something that we didn't have in our equilibrium model, but it's pretty important. And so we need to think about what effect that has. It turns out that putting these into a picture sets up the tide behaving like a large rotating wave. This rotation completes all the way around our part of the ocean, the basin, once in just over a day if it's diurnal, and twice if it's semidiurnal or mixed. We'll start with something relatively simple for our dynamic model. We'll have a square ocean, which is not too realistic, but it does have edges, unlike our equilibrium model, so it's a little more realistic. And we'll consider how the water behaves under that situation, taking into account the Coriolis effect, which we left out of the equilibrium. Okay, so we've got the tide, the Earth is spinning, it heads towards the east, that's why sunrise is in the east, and so that tidal bulge is going to end up pushing up against the west side of our ocean. But water is not good for trying to make a hill out of. It will try to drain back. But while that water is trying to drain back to the east from being up against the west side, the Earth is spinning, taking into account the Coriolis effect. It's going to instead, here in the northern hemisphere, end up going off to the right. So instead of heading east, it ends up against the south side of our ocean. Once again, we've piled up water. It's going to try to drain away, this time heading north, and the Earth's still spinning. So it ends up off to the east instead. Extra water to the east tries to drain west, Coriolis, and it ends up heading north. Extra water to the north tries to drain south, but Coriolis spins it off once more to the west. So we've got the water sloshing around in a circle, alternating, going up towards each of the sides here. Again, that's northern hemisphere. For southern hemisphere, it would be going to the left. And so we'd have the opposite pattern of sequence of sides. So all this makes for a rotating system where we have high and low tide on opposite sides of our part of the ocean, the particular basin there. Here in the northern hemisphere, the tide rotation pattern is counterclockwise. So it's a special type of wave. And this system with the complex waves is known as an amphidromic system. The wave circles around a node. The node is the spot in the middle where there's no up or down. The antinode, where we have the greatest amount of up and down, is at the edges around the shores of our basin. It has some components like a Sage type wave, but also like a moving wave going on. You can try making one if you have a round cup, say, with some water in it. Gently sloshing around, rotating a bit, will set up a rotating wave. And you can see one side's high, one side's low as it turns around. That's probably a good spot to pause here.